In this lecture, we will discuss geometrical isomerism, one of the stereoisomerisms. So, we are discussing about the stereoisomerism in the last classes, and stereoisomerism is classified into conformational isomerism, which is obtained by the free rotation or ring flipping, and the other kind of stereoisomerism is the configurational isomerism, where the isomers are obtained by the bond breaking or bond formation. So the configurational isomerism is further classified into geometrical isomerism and optical isomerism. So in this lecture, we will see what is geometrical isomerism. Okay, so consider a carbon-carbon double bond, and carbon has valency of 4, and 2 of its valencies are satisfied here when it forms a double bond. The rest 2, suppose this carbon atom has one atom or group denoted by A, and the other one is B. The other carbon atom also has the same A group here and the B group here, and these groups are arranged in this manner. That means A groups are arranged in the same side of this carbon-carbon double bond, and B groups are arranged again the other side of the carbon-carbon double bond. So this is a kind of spatial arrangement where similar atoms are arranged in the same side. Whereas if you see this structure here, the same carbon-carbon double bond backbone, and the similar atoms or groups are arranged in the opposite side. Here you can see if A is here and the other A is here, and B is here and the other B is here. So it's the same molecule, but the atoms attached or groups attached to the carbon atoms are arranged either on the same side of the carbon-carbon double bond or opposite side of the carbon-carbon double bond. So these two are isomers. These two are different spatial arrangements, and this form where the similar atoms are arranged in the same side of the carbon-carbon double bond, we call it as cis isomer, and this is the trans isomer where the similar atoms or groups are arranged in opposite side. So this is a trans isomer. And again, suppose you have A, B, two different atoms attached to the carbon atom, and the other carbon atom has the same A. One of the atoms is similar to what this carbon atom has, and suppose the fourth atom is D. Still, you will get cis isomer and trans isomer. So what I mean is a carbon-carbon double bond with this configuration also can give you cis isomer and trans isomer, whereas a molecule with this structure where all atoms attached to the carbon atoms are similar, then there is no point of geometrical isomerism, because this carbon atom has two A groups and this carbon atom also has two A groups. So it doesn't matter where the A groups are arranged. All configurations will give you the same spatial arrangement. So there is no geometrical isomerism in this case. Also here also, if this carbon atom has two similar atoms or groups, and the other carbon atom has one of the atoms or groups attached is different, again there won't be any difference in the spatial arrangement. So this molecular formula wouldn't give you cis isomer and trans isomer. Okay, so the question is how this isomerism is originating, or how these isomers are arranged differently in space. So you consider a carbon-carbon double bond here. So I have shown only single bond now, which is sigma bond. So you know that when a carbon forms a double bond, one of the bonds is the sigma bond, and now you can see that the atoms are arranged, and this is a cis isomer because the similar atoms or groups are arranged in the same side. So this is cis isomer, And this is a trans isomer where the similar atoms are arranged in opposite direction. Oh, sorry, here you have B, atom B or group B here. So I forgot to show that. Okay, so why this isomer situate like cis, and why this is trans, or why the conversion from cis to trans is not happening? That is because we have already seen that. So it's a double bond means a pi bond. Pi bond is sideways overlap, which is perpendicular to the sigma bond here. So this sideways overlap restrict the rotation of this bond. So if this bond rotates, then you will get this isomer from this, or if the rotation is possible, these structures are interconvertible. But the rotation is not possible in a double bond because of this pi bond, which is a sideways overlap. So that overlap restrict the free rotation of the carbon in this bond. So therefore, cis isomer remains as cis, and trans isomer remains as trans always, unless these bonds are break and form new bonds. So you cannot convert this isomer to this isomer without breaking the bond and form a new bond. So this restricted rotation, what we call this restricted rotation, is the reason for the geometrical isomerism. So you can define geometrical isomers as the same structural formula but differ in the spatial arrangement of atoms or groups around a double bond due to restricted rotation. So that is geometrical isomers. So these are geometrical isomers because these two molecules has the same structural formula and they differ in the spatial arrangement. Here you can see that similar atoms are on the same side, whereas here the similar atoms are in the opposite sides. So that is different spatial arrangement, and this arises due to the restricted rotation around a carbon-carbon double bond. So this is geometrical isomers, and this phenomenon is called geometrical isomerism. Okay, so these molecules are familiar to you because we have discussed about these molecules in our first class. So this is trans butene and this is cis butene. So this is trans butene because here the CH3 groups are arranged opposite sides around a carbon-carbon double bond. So this is the trans isomer, and here you can see that the CH3 groups are arranged on the same side of this carbon-carbon double bond, and this is the cis isomer of butene. Okay, so since they are two different isomers, they have difference in their physical properties. So let's see some of the physical properties where these molecules differ because of these spatial arrangements. It's very interesting to see. So if you take the melting point of these molecules, so melting point of trans butene is 167 Kelvin, whereas the melting point of cis butene is 134 Kelvin. So this difference in melting point is because of the difference in their spatial arrangements. So one thing you have to remember that these molecules are same in their molecular formula and the structural formula. They differ only the arrangement of atoms attached to the carbon atoms, and because of that difference in arrangement, the melting point of these isomers are different. So the reason why cis butene has a lower melting point is, so melting point is the temperature where a compound from its solid state goes to liquid state. Okay, so when this molecule goes to its solid state, the cis isomer has poor crystal lattice fitting. So that means because of the difference in the symmetry, I mean, you don't have to worry about too much about that symmetry thing, but what you have to remember is because of the symmetry considerations, in a crystal formed by cis butene, the packing is not perfect. So it's a poor crystal lattice fitting. So that means this cis butene in its solid state easily goes to the liquid state. I mean, easily means at the temperature of 134 Kelvin, whereas in trans butene, in its crystal form, when it forms its crystals, the individual molecules are arranged perfectly or packed perfectly
So that gives its more strength, I mean, in its crystal form, and that needs more energy to go to the liquid form. So that's why the melting point of trans-butene is higher than cis-butene. So in general, a trans isomer has higher melting point than a cis isomer. Okay, so when it comes to the boiling point, the situation is totally opposite. So here you can see that the trans-butene has a boiling point of 274 Kelvin, whereas the cis-butene has a boiling point of 277 Kelvin. So there is a slightly higher boiling point for cis-butene. The reason is cis-butene is slightly polar compared to trans-butene. So what is polar mean is it has a dipole moment of 0.33 dB. So what is dipole moment? I mean, if you examine these molecules, for example, if you take trans-butene, here the CH3 group is a plus I group, means inductively the CH3 group can donate an electron intensity in this direction. Here also the CH3 group will donate an electron intensity this direction. So that means there is a separation of charge because of this electron intensity donation. But if you take the resultant vector, so this is a vector quantity. So if you take the resultant of this vector, that nullifies. So therefore, the trans-butene has a zero dipole moment. So whereas in cis-butene, here again both CH3 groups will donate electron intensity here, but if you take the resultant vector, that will be in this direction. So that has a polarity, I mean dipole moment of 0.33. So polar means, or it has a dipole moment means there is a charge separation, maybe slightly higher negative charge here and slightly positive charge here. So that makes this molecule polar compared to its trans isomer. So this polarity makes its boiling point higher, means because of this polarity, the molecules, different molecules of cis-2-butene has a weak interaction. So that interaction makes its boiling point slightly higher than the trans isomer, trans-butene. Okay, and if you see the stability of these isomers, the trans-butene is more stable than cis-butene. The reason is, in cis-butene, the CH3 groups are on the same side and they are very close to each other compared to trans isomer. So because of this closeness, there is stereohindrance or crowded atmosphere is there. So that makes this molecule discomfort compared to this trans isomer. So cis-butene is less stable compared to trans-butene. So this is very interesting that the same molecular formula and same structural formula, but the difference in spatial arrangements of atoms around a carbon-carbon double bond makes the physical properties of the isomers different. Okay, so that means you can identify, if you give trans-butene or cis-butene, you can identify whether it's a cis form or trans form by looking at its melting point. Either you can look at its melting point and or the polarity or dipole moment, if whether the molecule has a dipole moment or not. So doing that, you can identify whether the isomer is cis form or trans form. Okay, so here another example, which is cis-butene 1,4-dioic acid or maleic acid. So it's a carbon-carbon double bond is here, and total 4 carbon atoms because it's but. So starting from here 1, 2, 3, 4 carbon atoms, and but-2-ene. So there is double bond at second carbon atom, 2-ene, and 1,4-dioic acid. So first carbon atom, that is a COOH group, carboxylic acid group. So 1, 2, 3, fourth carbon atom is also a carboxylic acid group. So this molecule is but-2-ene 1,4-dioic acid, and this is cis form because the similar groups are arranged in the same side of this carbon-carbon double bond. So this is cis isomer, and this is what we call maleic acid. And its trans isomer is fumaric acid which is trans-but-2-ene 1,4-dioic acid. So if you compare the melting point and the stability of maleic acid and fumaric acid, definitely, now you know from the previous slide that this maleic acid has lower melting point and stability compared to fumaric acid, because in maleic acid, this is cis form, and since its crystal has poor packing, poor fitting in crystal lattice, so therefore it has lower melting point, and it has lower stability as well, because the COH group is a bulkier group. When it comes on the same side, because of the closeness of these two COH groups, its stability is less compared to the fumaric acid. Now, another point is here in cis form, the two COH groups are coming closer. So there is a strong chance. So when you heat this molecule, these two COH molecules can condense and remove one molecule of water to form an anhydrate. So that means cis isomer or cis but-2-ene 1,4-dioic acid or maleic acid that readily yields anhydrate on heating above its melting point. So this is structure of anhydrate formed from this maleic acid. So when it comes to the fumaric acid, since it is transformed, these COH groups are far apart. So the condensation from these two COH of water molecules, elimination of water molecules from these two COH groups is not easy. So therefore, you can also convert this fumaric acid to maleic anhydride by heating it higher than its melting point. But anyhow, you have to give more temperature. You have to give more heat for this conversion. So first, this fumaric acid will convert to maleic acid. Then after that, you will get the maleic anhydride. So that what I mean is here the anhydride formation is very easy because these two COH groups are closer to each other. So it's easy for the water molecules to eliminate to form the anhydride. So this is also another example for how the trans and cis isomers differ in their properties because of the difference in the spatial arrangements of atoms or groups attached to the carbon-carbon double bond. So this is all about the geometrical isomerism. Thanks for listening to the lecture.